Andrew Dennis from Terrain NRM in North Queensland is going to explain to us how they're using satellite imagery to detect and map noxious weeds for treatment. Andrew, over to you. We can see your slide.
Thanks, Justin. This is what I'm going to describe to you today as part of an NHT-funded program, which is more than just working on these weeds. It's looking at a few other threatened species. But today we're just going to talk about one component of that project. And the reason for managing this particular weed, which is the wild tobacco bush, not the wild tobacco weed, it's different plants, is because it has a significant impact on one of our most threatened animals, spectacled flying fox. It's in DEQ's top priority threatened species. It's an important seed disperser and pollinator associated with tropical rainforests. It also forages and has ecological impacts in the nearby eucalypt forests just outside tropical rainforest boundaries. It is endangered throughout its entire global distribution, so around New Guinea and eastern Indonesia as well. But in Australia, it's undergone a more than 80% decline over the last 50 years, measured in this graph by CSIRO. Prior to 2004, in the late 90s, there were actually 850,000 bats counted or estimated. So that's a massive decline. In 2019, there were only 54,000 left after 23,000 died in a heat wave. So the second biggest mortality factor is an association between their foraging on the wild tobacco bush and coming in contact with a paralysis tick. They're not a natural host for the paralysis tick, so they have absolutely no immunity. Most of our native animals do, but the flying foxes would not normally forage down low where the ticks reside. We've done a whole lot of measures to determine that about 0.4% of feeding bouts of a bat on a tobacco bush would result in a bat getting a tick. The tick season, where the adults are questing, looking for hosts, is about 90 days at the end of the year. And in a camp last year near Yungaburra, there were more than 14,000 bats. So we would estimate that about 5,000 bats would pick up ticks off these bushes if every bat fed on tobacco bush every night. The reality was that 1,152 bats died in the tick season last year, which suggests that some might be dying away from the camp where we don't find them, and not every bat is eating tobacco fruit every night. The foraging on tobacco fruit coincides with the breeding season. So on the left, you can see the results of the adult bats getting tick paralysis, but there's also now more than 300 orphan babies in care, hopefully to be released later this year. Later this month. So, big problem, lots of bats dying. It's a problem that's restricted to the Atherton tablelands where this weed is particularly abundant. It's actually where the weed was first introduced, and it was introduced to attract fruit bats away from tropical fruit orchards. It's worked, though the bats still go to the fruit orchards as well. So we wanted to map and control the tobacco bush to break this association over 1,000 square kilometres of the Atherton tablelands. The most cost-effective way of doing that mapping was with high-resolution satellite imagery, given the area we were trying to map in detail. So we used some ground-truthed tobacco bushes to develop a model that used the spectral data from satellite imagery to classify the vegetation types using a spectral angle mapper. So we developed 13 classes of vegetation that were mapped, and one of those classes matches the reflectance of wild tobacco bush. So if we look at that image on the left, the bush itself has quite large leaves and they're very hairy. So in the central images, you can see these grey signatures in the aerial photograph. Those are wild tobacco bushes. They're reasonably distinct in the landscape. The images on the right show the different vegetation classes that our model developed, and the red was the one that reflected the wild tobacco bush. And the other shades of green and yellow are other vegetation types. In the lower right image, you can see sometimes other things have the same reflectance as tobacco bush. So there's a highway running along there, which is obviously not a tobacco bush, but it's in that same spectral range. So it's not 100% accurate, but it's pretty good. What we did then was, rather than putting all of those vegetation classes into our GIS system, we just took the wild tobacco class of spectral data and put that into the GIS system, and we've changed it to yellow instead of red. And it identifies on the landscape where high density patches of tobacco bush are, and it's helped us to develop a weed management plan. If we just focus in a little on this linear feature in the landscape there, you can see the image at the top on the right. The little yellow squiggles are polygons suggesting there might be wild tobacco there. And the image below that is the Queensland Globe fairly high resolution aerial photography. And you can see the silvery crowns of all the tobacco bush along that linear feature, which is what the model predicted. You can also see the model predicted stuff out in the paddock here. Some of that is wild tobacco bush. Some of that is old mature Guinea grass. So it's about 80% accurate. We do get some false positives, and that means it requires a bit of ground truthing. So we identify where in the landscape is a priority to go and control based on our mapping. We might also add some other layers, such as where the bat camps are, where the foraging zones of the bats are, and then go and drive around and check whether the model is accurate. And we can actually, on our mapping portal, delete the false positives from the layer. And then we use that to work with our partners, such as the Tablelands Regional Council, who are going out killing the weed for us. And we help work planning and identifying where are the priority places to start to protect the bats. They've added this species as a significant species in their biosecurity plan, which was an important step. They have direct access to our mapping portal because they also have a GIS license, and they're able to record the data of where they've been to control the plants, how many stems they've killed, straight into our mapping portal and give the data straight to us. And they can go on all land tenures to do that. Because the plant is in their biosecurity plan, we now have a partnership with Main Roads as well. So Main Roads are funding TRC to do the same work on the state roads, and we're funding them to do the private land and the council roads. We're in a process of developing a partnership with all of the traditional owners whose land we're working on. We're developing a model where they have employees from each mob on a team, where the regional council provides the equipment and the training and the supervision to have a team go around the 1,000 square kilometres and kill all the weeds. And that program will continue until mid-2028. And alongside it, we'll be monitoring tick mortality in the camps to see if we're having an impact. And I'll leave it there.
Thank you, Andrew. That's fantastic.